Welcome to The Explainer. Today, we are digging into a really fascinating conceptual design for a quantum machine. And this isn't just any design. It's a blueprint that tries to solve the single biggest problem in quantum computing, and it does it by pulling ideas from fractals, ancient math, and even the Fibonacci sequence. So, let's just start with the absolute core challenge, the question at the very heart of his quantum revolution. I mean, building a quantum computer is one thing, but how do you build one that can run these incredibly complex calculations without messing up? That's the real goal.
You see, the quantum computers we have right now, from places like IBM and Google, they exist in what we call the noisy intermediate scale quantum era, or NSQ for short. Basically, they're super powerful, but also incredibly fragile. The dream, the end goal, is to build a truly fault-tolerant machine, one that can literally correct its own mistakes on the fly. And this new 377-qubit blueprint, well, it might just be a huge step in that direction.
All right, so here's our game plan for this explainer. First, we're going to tackle that quantum error problem head-on. Then, we'll get into the blueprint itself. The Fibonacci part is super cool. We'll break down the four main pillars of its design. After that, we'll see how it all clicks together, and finally, we'll talk about what this could all mean for the future. Okay, first things first. We have to understand the single biggest thing holding quantum computing back, and that's noise. You can think of it like a constant static, humming in the background, messing with the super delicate quantum states that these computers absolutely depend on. And that's the reality we live in right now, this NISQ era. Even the tiniest disturbance from the environment, I'm talking a slight change in temperature, a random electromagnetic field, can create these errors. And then they just build up and can totally wreck a calculation. It's like having the handbrake pulled while you're trying to accelerate. So, let's get to the proposed solution. And this is where it gets really interesting, because it finds its inspiration in some places you would never expect, blending some seriously advanced physics with mathematical patterns that are thousands of years old. The whole design, everything we're about to talk about, is built around this one number, 377. And it is not random at all. It's basically the mathematical soul of this entire machine. So what is so special about 377? Well, it's the 14th number in the Fibonacci sequence. You know, that famous pattern you see in seashells and sunflowers and all over nature. But this isn't just for looks. The specific math behind this number is what makes it possible to arrange the qubits in a physical layout that is naturally resistant to noise. It's the key to the whole structure. So how does it all actually work? Well, the whole design is built on four big ideas. Four foundational pillars that all work together to create this amazing, self-correcting system. The very first pillar is the physical layout of the qubits themselves. It's called the Perez hourglass, and it's this beautiful fractal shape that actually comes from Pascal's triangle. It has this chaotic, messy-looking northern half, and then a much more orderly, structured southern half, which creates this incredible natural symmetry. Pillar number 2 is PHM. That stands for Perez Hourglass Associative Memory. And this is the error correction engine. The theory is that it's a perfect associative memory. That means it can take a noisy, corrupted piece of data and, boom, instantly figure out what the correct original information was supposed to be. And here's why PAM is such a big deal. We're talking about instant data retrieval. That's a massive, massive leap from the way we do things now. It's also incredibly tough. The theory says it can handle noise that messes up over 40% of the data. This just completely changes the game for fixing errors in quantum computers.
All right, pillar number 3 is the special kind of math that would actually run on the machine. These are called Perez-Pingala Mach-theta functions. And get this, it's a tool that connects the mathematics of ancient Indian poetic meter to the work of the genius mathematician Ramanujan. It's like a finely tuned instrument for controlling quantum operations with unbelievable precision. And the final pillar is something called quantum duality. Using that perfect symmetry of the hourglass shape we talked about, every single piece of logical information is encoded across two symmetric rails. The easiest way to think about it is like giving every bit of data a perfect twin for backup. It provides this built-in redundancy that just slashes the error rate.
So we've got these four pretty abstract ideas. How do they come together to actually form a machine, even a theoretical one? Let's take a look at how it's assembled. The architecture is broken down into 3 logical parts. First, you have the encoding module, which gets the quantum states ready.
Next, the computation module is where the actual quantum algorithm runs. And finally, the decoding module uses that powerhouse PAM system to find and fix any errors. It's like a clean, super efficient assembly line for quantum information.
And check this out. The way the 377 qubits are split up across these modules, it's not random either. The numbers line up almost perfectly with other Fibonacci numbers. 144 is the 12th one, 233 is the 13th, and the 99 for decoding is right next to the 11th. That mathematical elegance just runs through the entire design, top to bottom.
So, after all this theory, we have to ask the big question. Why does any of this actually matter? What would building a machine based on this radical blueprint actually mean for the real world?
Well, it really all comes down to efficiency. This design is aiming for a physical error threshold of about 1%. That's pretty similar to the leading method we use today, called the surface code. But, and this is the absolute key, it promises to get to that same level of fault tolerance with way less overhead. That means you'd need fewer physical qubits for every single error-corrected logical qubit.
This quote from the source document really just says it all. The potential here is that this design could give us a much faster, much more direct path to true, large-scale, fault-tolerant quantum computing. You know, the kind that can solve problems we currently think are unsolvable?
Now, of course, let's be clear. This is still a concept, a theoretical blueprint, but it is a remarkably detailed one. It brings together these deep concepts from math and physics in a totally new way. And it leaves us with a really exciting question. Could this strange, elegant, Fibonacci-inspired blueprint be the key that finally unlocks the full power of the quantum age?